So this is Group 8's video upload for problem 1.3 C and D. So this is the problem. So the first thing we're going to do here is we're going to define the coordinate system. So we have x1 on mass 1, and that goes to the right. That's positive. And we have x2 defined to be positive to the right for mass 2. So the first thing we're going to do here is create our free body diagram. So you have two masses, two springs, and a damper. So this is the force that is applied here, and it's to the right. So then because part of that force goes to accelerating mass 2, you have a different force on the left side of it. And these forces, F3, are equal and opposite. And so that is applied to the right side of the second spring. And because this spring is massless, then you have the same force on the left side of it. And because they're equal and opposite, that is also applied to the right side of mass 1. So then because part of that force goes into accelerating mass 1, you have two other forces on the left side, which we're calling F1 and F2. And again, they're equal and opposite. And you have the same force being on the left side of the damper and the spring because they are massless. So now, we're going to create the force equations. So for the damper, this is our equation. So that is F1, and it is C times x1 dot. And that's positive because it is in the same direction as our coordinate system here. Minus 0 because F1 is in the opposite direction of the coordinate system. Then for the first spring, you have F2 is equal to K1 times x1, and that's positive because this force is in the same direction as x1, minus 0. And then for the second spring over here, you have F3 is equal to K2 times x2, and that's positive because the force is in the same direction as x2, minus x1, and that's negative because these are in the opposite directions. Now over here you have Newton's law. So you have mass 1 times x1 double dot, which is the acceleration, equals the summation of the forces that are applied to it. So you have F3 being positive because it is in the same direction as the coordinate system, and F1 and F2 being negative since they're in the opposite direction. Now what we're going to do is we're going to combine these force equations and sub them in to these equations over here. So all we did is we just took these forces and subbed them into here to create these equations. And then you need to have the system on the left and your input on the right. So we moved these over here, we moved this over there to create these equations, which are in standard form. And those are the answers for part C.
Okay, so now we're going to do 1.3 part D. So this is your system, and you have two masses, M1 and M2. You have two dampers with damping constants C1 and C2, and you have two springs with spring constants K1 and K2. And then you're applying a force F to the right. So the first thing you have to do is draw your coordinate systems. So we have x1 defined here to the right, and x2 is also defined here as positive to the right. So next you're going to want to draw your free body diagram, which is right here. So on the free body diagram, make sure that you label all your coordinate systems. So again, x2 is labeled to the right and it's touched to mass 2. x1 is also labeled positive to the right and it's touched to x1. And the wall is just labeled as 0. And then you also have, since the springs are massless and the mass acts as a point mass, all of these are going to be the same coordinate. Since this is just a point mass, these are all connected. And same over here, this is also x2 and this is x2 because they're a point mass, and this is all connected. So the next thing you're going to want to do is label all your forces. So I started by labeling the force F over here, which is the input force. And then you want to label the forces that oppose F. So you have F1 and F2 here, which are acting in an opposite direction from F. And then you have the action-reaction forces on the damper and on the spring, which just act opposite direction of that. And then you have F2 here. And then same thing over here. You have F1 acting in opposite directions and F2 acting in opposite directions. And the reason that these forces are all the same is because the damper and the spring are both massless. So then on the mass you would draw the forces, and then you also draw the forces on the other side of the mass, but these forces are going to be different than what's on this side of the mass since the mass is accelerating. And then you just draw the action-reaction forces on the damper and on the spring. So once you draw your forces, you're going to want to write the equations. You're going to want to write the force equations for all of them. So here we have F3, which acts on this damper, and you define it, or you write F3 is equal to C1 times x1 dot, because F3 is going in the same direction as x1, minus 0, because that's just connected to the wall. And then for the spring with constant K1, you have F4 is equal to K1 times x1 minus 0, because F4 is acting in the same direction as x1. And then for the damper with this constant C2, you have F1, which is equal to C2 times x2 dot, because F1 is acting in the same direction as x2, and it's minus x1 dot, because F1 is acting opposite x1. And then finally you do your last spring, which has a constant K2, and you have F2 is equal to K2 times x2 minus x1, because F2 acts in the same direction as x2 but opposite x1. Next you're going to want to write the Newton law equations for the two masses. So you have for M1, it's M1 x1 double dot is equal to F1 plus F2 minus F3 minus F4, because F1 and F2 both go in the positive direction as defined by the coordinate, and F3 and F4 go in the opposite direction as defined by the coordinate system. And then for M2, you have M2 x2 double dot is equal to F minus F1 minus F2, because F is going in the same direction as the coordinate was defined, and F1 and F2 are going in the opposite directions. So now you're going to want to substitute and combine all of these equations that you have. So you would write the equations for F1, F2, F3, and F4 in here where they correspond. So you get M1 x1 double dot is equal to this, and M2 x2 double dot is equal to this. And then after you do that, you want to write it in standard form. So you want to combine all of the parts of the equation that correspond to the system over to the left, and you want to leave the input on the right. So you end up with this, and so you have everything that's part of the system on the left, and everything that's everything that's an input is on the right, which in this case is only F.